Now let's talk about how the slope is measured, methods of measuring slope. So basically we have two methods for measuring slope. And in these methods we use a window. I will explain that later, but let me first talk about method of calculation. So there are two methods of calculation. The first one is planar, while second is geodesic. In planar we use Cartesian coordinate system, while in geodesic we assume that the earth is ellipsoid, and for that we use angles. And for that the coordinate system is geographic, in which we assume that the earth is ellipsoid. And every point is represented by angles. Geodetic, we make use of geodetic coordinates, in which we have latitude, longitude, and height, height from mean sea level. This is known as geographical coordinate system, in which the earth is considered ellipsoid. Now among them, which one is more accurate? So the geodesic is more accurate. Okay, so I will roughly explain what happens in geodesic. In geodesic we transform, step one is that transformation of a geodesic coordinate. So suppose that you have your coordinates as following. So if you represent this by ellipsoid, it will be somewhat like this. This is the ellipsoid in one direction. This is another ellipsoid. Considering it to be 3D, it will be somewhat like this. So if you have a point and that point is this one, and this point is representing some terrain. So this location, let's call this as T. Its location will be xt, yt, and zt. Okay, and if you project this in fact this will be angles. So if I drop it down like this, I will use a black color for that. If I drop it down, so there is one angle subtending this vertical angle, and there is another angle subtending, which you can see like this. Okay, so let's call this as lambda and the vertical one as phi. This lambda is longitude, while this phi is latitude. So what we do is we transform this latitude, longitude, and h height into x, y, z, for which we have some functions. Okay, what are those functions? Those functions are following. X will be equal to n of phi plus h cos of phi and cos of lambda. Y will be equal to n of phi plus h cos of phi cos of sine of lambda, and z will be equal to b square. I'll explain what is b, divided by a square multiplied by n of phi plus h sine of phi, where n of phi is a function which is equal to a square whole divided by root of a square cos of phi square plus b square sine of phi square. Okay, where a is equal to major axis of ellipsoid, b is equal to minor axis of ellipsoid, So what is A and B here? In the diagram, if you see, so in the diagram, this distance, this one is known as A, and this vertical distance, this is the minor axis, and the major axis is the vertical one. This vertical distance, this one is B. Okay, the two axes, major and minor axis. So what happened is that if you use these equations, so you consider that your earth is ellipsoid like this. This is a portion of that, okay, and your surface is, earth surface, topographic surface is somewhat like this. So what you do is that you take a tangent over a point, okay, and this is known as a tangent plane, and it will have some height. This is the correct definition of height is actually the height of the datum, ellipsoid datum, from the topographic surface. This red is topographic surface. This is ellipsoid. This is the topographic surface. So this point is basically that t, xt, yt, and zt, and this thing is a normal, ellipsoid normal. So once you calculate this, then you start calculating slope. How the slope is calculated? The slope is calculated by fitting a surface which is represented by z is equal to ax plus by plus c. You try to fit this surface, and you try to fit this surface as I explained here, that you have this is your surface, okay. So you are trying to fit a surface which is represented by this equation, and you try to fit it over at the top of this, okay, at top of this. So how is that fitted? You know this point position, okay. Once you know this position, so what you do is that you bring in a surface at that position, at that very position, that this is z, let this be y, let this be x. So you try to bring in a surface. That surface will have 3 by 3 cells, okay, and you fit this surface at top of this very point, okay. So once you try to bring this surface at top of this point, which is represented by this equation, there will be difference of z value in each cell. Each cell will have its own z value, and each cell will also have a z value computed from this equation. Okay, so I will draw that. So some point may be below, here the computer point are below, okay, while some point will be above, like this one, and over here someone is like this and one is like this. So what you will have a difference. Okay, you will have a difference of z value at each point, which you can see is represented by this black line. Some are positive, some are negative, so they are known as delta z1, delta z2, delta z3, delta z4, delta z5, delta z6, delta z7, delta z8, delta z9. Okay, now then you try to minimize this delta z using a method known as least square fitting method, in which what you try to do, you try to compute this sum of delta z from 1 to 9. You take its square and you try to minimize it. This method is explained by David Eberle in 1999. Least square fitting of data, geometric tools, page 3. Okay, so this is a process of finding the slope. I will repeat, then you will understand it. In this process, what we do is that we have geodesic coordinates, in which we have angles, latitude, longitude, and height. We perform a transformation. In transformation, we convert the coordinate into x, y, z using some formulas. There is no need to go into the details of these formulas. It is just to make you explain. And once you transform your point, for example, our point data is our point is this surface, which I have circled. This surface, the center point of this surface will have some longitude, some latitude, and some height from the datum. So you convert that into x, y, and z using the formula. Okay, and then here, which you can see, and then at top of it you fit a surface represented by this equation, which will look somewhat like this. Okay, and when you fit at top of this a surface, this surface will be represented by a cell of 3 cross 3, which you can see here, 9 cells here. And when you try to fit a surface, then there will be a difference of z value. That z value, one is the original z value of each cell. The original z value of each cell will come from the original surface here, original elevation file. And one is the computed z value. The computed z value will come from this surface when you fit in, which is represented by in each cell it is represented by dz1, dz2, dz3. And then you try to minimize this using a method explained by David Eberle. So with the help of this, you get a surface. What result you get? With the help of this, you get a surface. I will draw that here again. That you have a datum, and then you have a surface, topographic surface, and then you have a tangent plane, and at some height you get a surface. This is the desired surface which we get, and this surface will be at some slope. The above one here, this is ellipsoid normal. The second one is surface normal. Normal of the surface, normal with respect to ellipsoid, it will be at just normal to the surface will be the normal of this one, okay, which will be subtended on the surface, while normal ellipsoid will be the one which will be with respect to the tangent over here. Okay, so this will give you some angles like beta, which is the angle between ellipsoid normal and surface normal, and another angle which you will get the normal of surface will be with respect to the tangent on the surface. This is the tangent on the surface. While this one is the tangent at ellipsoid. Okay, so the angle between the two, the angle between the normal of the two is known as beta, while the angle between them is known as alpha. So what is slope? Basically, slope is angle will be, the slope angle will be this beta. Okay, so if I summarize this method once again, so in this method, in geodesic method, we have angular coordinates, we have geodetic coordinates having latitude, longitude, and height, altitude. We transform this coordinate into x, y, z, At that particular xyz, we try to fit a curve represented by this equation. And when you fit a curve at your cell, which is represented here, you take a cell grid of 3 cross 3, total 9 cells, at the center of which you try to fit this equation. Okay, so as a result, when you try to fit that, you will get a difference of z value. One z value will be computed z value, the other will be the original DEM value, elevation value. So you try to minimize this difference. Okay, and then this surface will subtend, this surface which you get will subtend an angle on the topographic surface, okay, with respect to tangent of ellipsoid. And how you compute this? You compute this by taking the angle between the normal of tangent of ellipsoid. This is the normal of tangent of ellipsoid. This is the tangent of ellipsoid. This is the normal of tangent of ellipsoid. And the normal of the tangent of the surface. This is the tangent on the surface, and this is the normal of tangent of surface. The angle between these two will give you beta, and this beta is slope.